This lecture is on solving equations. This is a big idea in math. There are lots of different kinds of equations we can solve. In this lecture, we'll actually only talk about solving a few specific types of equations. But before we move into the specifics, we want to talk a little bit about what it means generally to solve an equation, because these ideas will be applied to all kinds of different equations in this class and in future classes. So, what does it mean to solve an equation? Well, let's start out with a few definitions. Solving an equation basically just means finding all of the values, which when we plug them in for the variable or variables, if there's more than one, make the equation true. And in particular, we'll call this set of values the solution set. So let's look at a couple of examples to help us better understand this definition. In particular, let's suppose we have the equation 2x equals 6. And we want to solve for x. That means we want to find all the values that we can plug in for x that will make the equation true. Well, we'll find that the solution set for this is when x equals 3. Because 3 is the only value that we can plug in for x to make this equation true. We can see that this is a solution by plugging it in. We take the 3 and put it in where the x used to be. And we do in fact find that 2 times 3 equals 6. So we get 6 equals 6. That's definitely true. So we can see that is in fact a solution. Here's another example. What if we have this, where they ask us to solve for y, and the equation is actually x plus y equals 1. What values can we plug in for y to make this equation true? Well, this is a little more complicated because in this case we have two variables. So there's some different ways that we can think about it. But one particular way we can think about it is what happens if we have y equals 1 minus x. Well, if we plug in 1 minus x in for y into this equation, it will certainly make the equation true. Let's check and see that that's the case. So I have x plus y equals 1 is my original equation. And where I had the y, I'm now going to plug in 1 minus x. If I simplify this, well, I'm saying x plus 1 minus x. I can rewrite that as x plus 1 plus negative x. And now that this is all addition, I don't need the parentheses anymore because I can add things in any order. So I get x plus 1 plus negative x equals 1. And of course, I can rewrite addition in any order, so I can rewrite this as x plus negative x plus 1 equals 1. And so of course, this x plus negative x is just 0. So I certainly get that 1 equals 1. That's certainly true. And so I can see that the value that I can plug in for y here is 1 minus x. Now that's not a constant value. It depends on what we might put in for x. So because we have two variables, there are several options. We can see here, for example, that if x were 1, the value that we could plug in for y to make the equation true would have to be 0. Or if x were 0, the value we'd have to plug in for y would be 1. If x were 1/2, the value we'd have to plug in for y would be 1/2, and so forth. So, how does this actually help us know how to solve equations for a particular variable? Well, we can summarize it this way. Most techniques for solving equations involve replacing the original equation with an equivalent equation. And why would we want to replace the original equation with an equivalent equation? Well, usually we want to replace it with an equivalent equation that is actually simpler. And in fact, this usually requires several steps. In which the equation from the previous step is replaced with an equivalent equation, which is simpler. So, when solving equations, what is our ultimate goal? The equations that we obtain in the final step should be formatted in such a way that the variable that we're looking for, the variable for which we're trying to solve, is all by itself on one side. So, for example, if we're solving for x, we might have x equals negative 2.6. That's one example. If we were solving for n, we might have an equation where we get something like this. N equals PV over RT. There are lots of variables on the right, but if we want to solve for n, our main interest is getting n by itself on one side, and that's what we've done here. N is by itself on the left-hand side of the equation. Here's another example. If we were solving for y, might have negative 48 equals y. Again, this is solved for y because y is by itself on one side. It doesn't have to be on the left-hand side. It could be on the right-hand side. We'll just follow this up with a note here. When we replace one equation with an equivalent equation, we often say colloquially that we are moving things around in the equation or rewriting the equation a different way. Technically, when we talk about moving things around in an equation, or when we talk about rewriting an equation, what we really mean is that we're taking the original equation and we're replacing it with an equivalent equation. But we'll often, because it's easier to talk about it, we'll often use these terms. We'll often say that we're moving something around. And we just want to keep in mind that what we're really doing is we're taking an equation and converting it to another equation that has the same solution set. And because what we're interested in is the ultimate solution set, we don't actually care which of the possible equivalent equations we have in front of us. We're happy replacing one equation with an equivalent one because our final point of interest is the solution set we'll get at the end. So why are we interested in solving equations in the first place? Well, one of the major reasons we often use mathematics is because it can be used to model lots of real-world behavior. So there are lots of different equations that can be used to model particular behavior in the real world. So here are just some examples of some of these types of equations, and in particular some examples that we're going to encounter in this particular lecture. In future lectures we'll encounter other kinds of equations. So let's look at some examples. If you look at the taxi cab fare in New York City, based on the number of miles. In Manhattan, based on the number of miles driven. We could write an equation like this. Because the taxi charges $2.50 initially and then about $2 for each mile. Here's another example. Speed of a falling object. When it's dropped from a height of 50 feet. At time t. So how fast is it going at time t? Well, we could write an equation like this. And that would tell us what the speed is. Here's another kind of equation we might see. we want to calculate the surface area of a cylinder with radius r and height h. That surface area is represented by the letter s. Then we could write it in an equation like this. S equals 2 pi r squared plus 2 pi r h, for example. So, if we want to be able to solve equations, we're going to need to have some techniques that help us figure out what we can do to equations without changing the solution set. Because we want to take the equation that we're given and replace it with equivalent equations, we need some techniques for taking one equation and turning it into an equivalent equation. And the only way to take an equation and turn it into another equivalent equation is to figure out what we can do to an equation without changing the solution set. So let's think about what some of those things may be. And before we get started with that question, I would just want to define a little bit of notation here. I'm going to define this arrow notation. If I write something P and then an arrow pointing at Q, whatever P and Q may be, they might be equations or statements or something. All this means is that if P is true, then Q is true. It means essentially that Q follows from P. Which is basically what it looks like. Similarly, if I have the arrow going both ways, it just means it works in both directions. If P is true, then Q is true. If Q is true, then P is true. P follows from Q, Q follows from P, essentially. So this means it works both ways. Okay. Nothing too fancy. It's basically what it looks like. But it's a nice quick way of writing that one thing follows from another. Okay, so back to our central question. What can we do to an equation without changing the solution set? So we want to think about that. Can we come up with a couple of things that we can do? Well, one of the things we may notice that we can do is we can add anything we want to both sides. And that won't change the solution set. And if we want to write that out using math, we could say, for any three algebraic expressions, A, B, and C, say, if I have A equals B, well, I could certainly get A plus C equals B plus C directly from that by adding C to both sides. And actually, it should work the other way as well. If I have A plus C equals B plus C, then I know I have A equals B. So this tells us that fundamentally we can always add something to both sides without changing the solution set. And we want to write a little note here, actually. Remember that we can rewrite subtraction as addition. We can rewrite subtraction as adding a negative number. we can extend this idea to subtraction also. So we could say if c were negative and we added it to both sides, it would be like the same thing as saying we can subtract whatever we want from both sides, and it won't change the solution set. What else could we do? Well, we might notice that we can multiply both sides of an equation by almost anything. By anything except 0, without changing the solution set. So, for example, for a non-zero c, we'll get if a equals b, then ac equals bc. And in fact, that actually is true also when c equals 0. But we want the other direction to be true too. If we have a times something equals b times something, as long as that c isn't 0, we know that then we have a equals b as well. So multiplying both sides of the equation by anything other than 0 doesn't change the solution set. Notice, if you multiplied both sides of an equation by 0, how would it change the solution set? Well, if you multiplied both sides of the equation by 0, then anything you plug into the equation would make it true. Because you would just end up with 0 equals 0. And 0 equals 0 is always true, no matter what values you plugged in for any variables. So we do have to be careful that c isn't equal to 0 when we do our multiplication. Otherwise, it will change the solution set. And so, similarly to the case for addition, we want to point out division can always be rewritten as multiplication. You just multiply by the reciprocal. Dividing by 2 is the same thing as multiplying by 1/2, for example. So we can extend this idea to division also. So that means we can divide both sides of an equation by any number that's not 0. Obviously we can't divide by 0 because that would be undefined. And it won't change the solution set. Now there's one word of caution here. I want to note that if each side of the equation has multiple terms, you have to be sure to multiply every single term on each side by c. So we'll have to distribute c to every term on both sides of the equation. So for example, if we had 3x squared plus 2x equals 8 minus 4x, and we wanted to multiply both sides by 2, what will we get? Well, we have our 3x squared plus 2x equals 8 minus 4x. And we can go ahead and multiply both sides by 2. But if we do that, we need to distribute the 2 to every single piece on each side. So we should end up with 2 times 3x squared plus 2 times 2x on the left. And on the right, we should end up with 8 times 2 plus negative 4x times 2.
So, we have some rules or patterns that tell us some things that we can do to equations without changing the solution set. And that's important, because the only way we can solve an equation is to replace it with an equivalent equation that looks simpler. But the problem is, how do we know when to use which rule? So we need to think about, how do we decide what to do to an equation? And more specifically, given the rules that we know about, when should we add or subtract or multiply or divide, right? When should we add, subtract, multiply, or divide? Which one should we use? Which operation should we use? And how do we pick the number that we actually add, subtract, multiply, or divide, or the expression that we actually add, subtract, multiply, or divide to each side? So these are the big questions. And in order to answer them, we need to think about what specifically we want to move in that particular equation. Once we've identified what we want to move, we just need to ask ourselves a couple of questions. What is that thing we're trying to move currently doing in the equation? Is it being added, subtracted, multiplied by something? Is it dividing something? And then the second question we need to ask ourselves is, what is the opposite of what it's doing? We will want to do
the opposite of whatever that is to both sides. So let's look at some examples to understand what we mean by opposites. So let's suppose that I have the equation 2x plus 2y equals 10, and I want to move the 2y. What will I need to do in order to change this equation so that I can move the 2y? Well, first I notice the 2y is being added in this equation. So the opposite would be subtract 2y. So the opposite of adding 2y is subtracting 2y. Or we could think of this as adding negative 2y. If you want to think of everything as addition. So I want to subtract 2y from both sides of the equation. So I have 2x plus 2y equals 10 to begin with, and I subtract 2y from both sides. And so what ends up happening? Well, 2y minus 2y is equal to 0, so I get 2x plus 0 equals 10 minus 2y, which is of course just the same thing as 2x equals 10 minus 2y. So we can see in a sense that now the 2y is on the other side. You could say in a sense it has been moved to the other side. Of course, more formally what we've done is we've taken this equation 2x plus 2y equals 10 and we've replaced it with the equivalent equation 2x equals 10 minus 2y. And again, these two equations are equivalent because they have the same solution set. Let's look at another example. Let's suppose we have n over 3 equals 27 plus n. And let's suppose I want to move the 3. So we need to think about our important questions. What is the 3 currently doing? The 3 is currently dividing the n on the left. So the opposite would be to multiply by 3. So I want to multiply both sides by 3. So if I started out with n over 3 equals 27 plus n, I have to be very careful to multiply the whole thing by 3. The whole thing by 3. And I can write 3 as 3 over 1. That's the same thing as 3. And so, of course, if I do that, I get 3n over 3 equals, here I need to distribute this. So 3 times 27 plus 3n. So we get 3 divided by 3 is actually just 1. We get 1n equals 81 plus 3n. And then, of course, 1n is just equal to n. So we get n equals 81 plus 3n in this example. So we can see here what we've done is we've moved the 3 to the other side of the equation. Again, what we've really done is we've taken the original equation, n over 3 equals 27 plus n, and we've replaced it with an equivalent equation, n equals 81 plus 3n. And they're equivalent because they have the same solution set. So we need to go back for a moment and talk about what we mean by this idea of opposites. What is an opposite? What does it actually mean to cancel something out? Well, it depends on the operation. When we're adding and subtracting, canceling something out means getting 0. And why is that? That's because adding 0 to something or subtracting 0 from something does not change it. So in a sense, if all we have left that we're adding to something is 0, we sort of have nothing else. This is different, though, when we're multiplying and dividing. When we're multiplying and dividing, canceling something out means getting 1, not 0. This is because multiplying 1 by something does not change it. So in a sense, if the only thing we're multiplying by is 1, we're sort of multiplying by nothing interesting. We've gotten rid of all the interesting stuff. This is really important to keep in mind. We want to be sure we're really aware that when we say we're canceling something, what we're really doing is getting 0 if it's addition or subtraction that we're focusing on. But if we're focusing on multiplication or division, when we say we're canceling something, we're actually getting a 1, because it's 1 times something gives us the same thing back. 0 times something does not. So it's important for us to pay attention. We use the word canceling in a sort of casual way, but what it really means is something more specific, and it depends on the context by what we mean when we say cancel. So now we have all the tools we need to actually do some examples. We have some rules of things that we can do to equations that will give us equivalent equations with the same solution set. And we have some ideas about when we should try to use these rules. We should look for things we want to move around in the equation, figure out what they're doing in the equation, and then try to do the opposite. And we just keep in mind that the opposite of adding involves subtracting so that we can get 0. The opposite of multiplying involves dividing so that we can get 1, for example. And so fundamentally, we just have to stop at each step in the equation and ask ourselves, what do I need to do to get the variable by itself in one side? What do I need to move? And that should inform what we want to do next. So let's try out some examples. In this example, we're going to solve for x. And we have 6x minus 4 equals 3x plus 14. So we want to get x by itself on one side. So I have something with an accent on the left, something with an accent on the right. Somehow I want to move one of these over to the other side. Doesn't matter which one, so I just pick one. I might decide to get rid of the 3x in this case, in which case I ask myself, what is the 3x doing in the equation? Well, it's being added to the 14. So the opposite of adding a 3x is subtracting a 3x. So I get 6x minus 4 equals 3x plus 14. And now on each side, I'm going to subtract 3x. Subtract 3x. So what happens? (6x) and negative 3x are like terms, so 6x plus negative 3x, or 6x minus 3x, is 3x. I still have a minus 4 left over. On this side I have a 3x and a negative 3x. Those two come together to equal 0, so they go away, and I get 0 plus 14, so all that's left over here is 14. Now I have 3x minus 4 equals 14. So the x is just on one side, but I've got some other things over on that side that I want to get rid of. For example, the minus 4 or the plus negative 4. So what's the opposite of subtracting 4 or adding a negative 4? Adding a positive 4 would be the opposite. So I take 3x minus 4 equals 14, and I add 4 to both sides. Negative 4 plus 4 is going to be equal to 0. So I have 3x plus 0, which leaves just 3x on the left-hand side. And 14 plus 4 is 18. The x is almost by itself, but I have this 3 here that is still next to the x that I need to get rid of. What is the 3 doing in the equation? It's multiplying the x by 3. So the opposite of multiplying by 3 is to divide by 3. So I can divide the whole left-hand side of the equation by 3 and the whole right-hand side of the equation by 3. 3 divided by 3 is just 1. So I get 1x equals 18 divided by 3 is 6. And 1 times x is just x. So I get x equals 6. So this should be my final answer. What have I done again? I've taken the original equation and replaced it with an equivalent equation. In other words, I've taken the original equation and replaced it with an equation that should have the same solution set. Well, the solution set of the final equation is simply x equals 6. So if I plug 6 into the original equation, I should still get a true statement. Let's try that out so I can check my answer. I'm going to rewrite the original equation just as it is, but I want to plug in values for x. So every place I see an x, I'm just going to put some empty parentheses. 6x minus 4 equals 3x plus 14. So now where all the parentheses are, I plug in 6. 6 times 6 is 36 minus 4 equals 3 times 6 is 18 plus 14. 36 minus 4 is 32. 18 plus 14 is 32. I get the statement 32 equals 32. That's definitely correct, so I know that my work is correct. 6 is indeed in the solution set for the original equation. Let's try another example. This time let's solve for y. Here my equation is 2 parentheses 3y minus 2 close parentheses plus 5 equals 8 minus 2y minus 5. In this problem, I want to get y by itself on one side, but I notice I definitely have y's on the left, and I definitely have y's on the right, and I have a lot of other things going on here as well. In this case, it clearly would be easiest if I just simplified each side first, and then I can try to move things around in the equation. So, in order to simplify each side, clearly distributing the 2 to each piece here on the left would help get rid of these parentheses, and on the right-hand side, I would like to be able to get rid of the parentheses, but I'm subtracting everything inside the parentheses. So the best way to think of this is to think of this as a plus negative 1 out on the front of this parenthesis. And so I can think of distributing the negative 1 to each piece. Okay, if I do that, what do I get? Well, 2 times 3y is 6y. 2 times negative 2 is negative 4. Now I still have the plus 5 equals 8 plus negative 1 times 2y is negative 2y. Negative 1 times negative 5 is positive 5. Now, negative 4 and 5 are like terms, so I can go ahead and add them. So I get 6y plus 1 equals, here 8 and 5 are like terms, so I can go ahead and add them. So 8 plus 5 is 13 plus negative 2y. So I've simplified each side as much as I can. Now I want to move all the y's together so they're on one side and try to get everything else on the other side. So here I have a y on each side. I have a 6y and a negative 2y. So I want to move one of those over to the other side. It doesn't really matter which one, so I might want to get rid of the negative 2y. So I have 6y plus 1 equals 13 plus negative 2y. Now I want to get rid of the negative 2y, so I want to do the opposite. What is it doing in the current equation? Well, it's being added to the 13. So what's the opposite of adding negative 2y? Well, the opposite of that would be adding positive 2y. So I can add positive 2y to each side. Negative 2y plus positive 2y is going to equal 0. So all I will have left on the right-hand side will just be 13. And on the left-hand side, I have 6y and 2y are like terms. If I add them together, I get 8y, and I still have the plus 1. So 8y plus 1 equals 13. Well, I want to get the y by itself, so I'm going to need to get rid of this plus 1. What is it doing in the equation? It's being added, so the opposite of adding 1 is subtracting 1. So 8y plus 1 equals 13. I can subtract 1 from each side. Plus 1 minus 1 is just going to equal 0. So I have 8y plus 0 is just 8y equals 13 minus 1 is 12. The y is almost by itself, but it has an 8 next to it. What is the 8 doing in the equation? The 8 is multiplying the y by the y. The y is being multiplied by 8. So the opposite of multiplying by 8 is dividing by 8. So we can divide both sides by 8. 8 divided by 8 is just 1. So we get 1y equals 12 divided by 8. Well, we can think of just simplifying both of these. We can certainly divide both of them by 2, and in fact we can divide them both by 4. So 12 divided by 4 is just 3, and 8 divided by 4 is just 2. So I get 3 halves. And 1 times y is just y, so I get y equals 3 halves. Okay, again, I can check that by plugging that into the original equation. If I want to check it, I again should start by rewriting the original equation. In every place I see a y, I leave some empty parentheses in which to plug in my values. So 2 times 3y minus 2 plus 5 equals 8 minus 2 times y minus 5. So now every place we had the y, we want to put in 3 halves. And now we can simplify some of this. We can write this as 2 times parentheses 3 over 1 times 3 halves minus 2 plus 5 equals 8 minus 2 over 1 times 3 halves minus 5. So if we do the multiplication, we get 2 times 9 halves minus 2 plus 5 equals 8 minus, we notice we have a 2 on top, we have a 2 on the bottom. If we divide them both by 2, we get 1 and 1 in these two spots. So 1 over 1 times 3 over 1 is just 3 over 1, or 3 minus 5 is what we still have in there. Okay, on the left-hand side, we have 2 times 9 halves minus 2. But we can go ahead and change the minus 2 to a fraction, so minus 2 over 1. And we want to get a common denominator here, so we have a 2 on the bottom of 9 over 2. So if we multiply 2 over 1 by 2 on the bottom and 2 on the top, we can get a common denominator. Same thing over here. We have 3 over 1 minus 5. Well, we don't need to write the 3 over 1 as a fraction anymore. We can simply write it as 3 minus 5. Okay. So we have 9 halves minus 4 halves on the left. Everything else stays the same. 8 minus 3 minus 5 is negative 2. Here on the left, 2 times 9 halves minus 4 halves is 5 halves, plus 5 equals 8 minus negative 2 is 8 plus 2. 2 times 5 halves we can rewrite as 2 over 1 times 5 over 2. 8 plus 2 is 10. And we notice 2 over 1 times 5 over 2, we can divide both the top and the bottom by 2 to get 1 over 1. So we get 1 over 1 times 5 over 1, which is just 1 times 5. So we get 5 plus 5 equals 10. That's absolutely true. So we've checked our answer, and we've seen that plugging 3 halves into the original equation definitely makes the equation true. Here's another example. let's solve for a. And here we have 6a minus 4 equals 2 times parentheses 8 plus 3a. So we want to get a by itself on one side, and we notice there's some stuff we could simplify here, so we probably want to do that first. We could get rid of the parentheses on the right hand side, so we could go ahead and multiply everything inside the parentheses by 2. So we get 6a minus 4 equals 2 times 8 is 16, 2 times 3a is 6a. Now we want to get a by itself on one side, so we need to move anything with an a in it over to one side. Doesn't matter which one. So for example, I could take the a on the left and move it over. So this 6a, what is it doing in the equation? Well, it's being added to negative 4. The negative 4 is what's getting subtracted, so the negative sign goes with the 4. So the 6a itself is being added. So what's the opposite of adding 6a? Subtracting 6a. So I have 6a minus 4 equals 16 plus 6a, and I can go ahead and subtract 6a from both sides. So what happens? 6a here and the minus 6a here, we add them together, we'll get 0. So what we have on the left will simply be negative 4. And the 6a minus 6a here will equal 0. So all we have on the left is 16 plus 0, which is 16. Well, we notice something interesting here. We've gotten the statement negative 4 equals 16. This is absolutely not true. While trying to solve for a, we actually eliminated the a's from the equation entirely, and we got a false statement. What does that mean? Well, this equation, negative 4 equals 16, has the same solution set as the original equation. And what is the solution set of the equation negative 4 equals 16? Well, the solution set is empty. There is no solution, because this is a false statement. No matter what we plug in for a, we're still going to end up with some statement that's not true. If we look farther up, we can see why this is the case. We have 6 a's on either side, so it doesn't matter what we put in for a, we're still going to end up with negative 4 equals negative 16 is fundamentally something that would need to be equal in order to make that equation true. And because negative 4 will never equal 16, we can never have something that we can plug in for a that will make any of these equations true, the initial equation or the final equation. So this particular equation, we'd have to say there is no solution. That would be our final answer. Sometimes you'll see people write the solution set as the empty set, which would be the set that doesn't have anything in it. You might see that in some cases. Let's take a look at another example. In this case, we'll solve for p. Here we have 2p plus 3 minus 8p equals 3 times 1 minus 2p. Again, we want to move all the p's over onto one side and try to get them by themselves. And so one of the things we want to do probably along the way is to simplify each side. It'll make it easier to move things around. So we can see on the left-hand side, I've got a couple of things with p in it that I could combine. I have a 2p, and I have a minus 8p. I might want to rewrite that, for example, as plus and negative. It might make it easier. So 2p plus negative 8p is negative 6p. And I still have my plus 3 here. Over on the right-hand side, I can distribute the 3 to each piece. 3 times 1 is 3. 3 times negative 2p is negative 6p. And so here, I want to get p by itself on one side. So I've got p's on each side. I'll need to get rid of one of them. It doesn't matter which one. Let's take a look here. I have negative 6p. What's the opposite of that? Of adding a negative 6p? Well, adding a positive 6p. So I have negative 6p plus 3 equals 3 minus 6p. If I add a positive 6p to each side, the negative 6p and the positive 6p here are going to add together to get 0. So I have 0 plus 3. So I'm just going to end up with a 3 on the left. And here, the minus 6p plus 6p also equals 0, so I get 3 plus 0, so I get 3. It's interesting, this is a true statement. So what does that tell me about the solution set? Well, the solution set of the equation 3 equals 3 has to be the same as the solution set of the original equation. Well, what is the solution set of the equation 3 equals 3? Well, it's all the values that you can plug in for p to make that statement true. Well, there aren't any p's here. The statement 3 equals 3 will always be true. It's always true no matter what you plug in for p. Why is that? We can see why. If we go farther up in the second step, you notice we end up with negative 6p on each side. So we can plug in a 0 for p, we can plug in an 8 million, we can plug in pi. It doesn't make any difference. Negative 6 pi is going to be the same on each side. Or negative 6 million is going to be the same on each side. So whatever we plug in for p, this is always true. And so the way we typically write this is we say the solution set is all real numbers. The solution is the set of all real numbers. We say all real numbers because in this class we're mostly just dealing with real numbers. With this equation we're only substituting in real numbers. We're not really permitting ourselves to consider imaginary numbers or complex numbers, which you might have seen in another class. But for sort of common purposes, pretty much any number we're likely to encounter in the real world is going to be a real number. The only kinds of numbers that are not real numbers are imaginary numbers, the letter I in it, or complex numbers that involve combining imaginary and real numbers together. Let's try a few more examples. In this case, let's solve for r. Now we notice that in this equation we actually have a whole bunch of variables. But that doesn't actually matter. We just need to use the same techniques as we did before. If we're solving for r, that means we want to get r by itself on one side. So anything else that's over on the side with r, we want to move. So in this case we have an n and we have a t. So we can tackle those one at a time, or we can try to do them both in one step. Since we're just starting out, let's try them one at a time. So I want to get rid of the n. What is the n doing in this equation? Well, n is being multiplied by the r. So what's the opposite of multiplying by n? Dividing by n. So if I've got PV equals nRT, if I want to divide both sides of the equation by n, I want to be sure to divide the whole thing. N divided by n is going to equal 1. So I have PV over n equals RT. Now still I want to get r by itself, so I need to get rid of this t. What is the t doing in the equation? Well, it's being multiplied by the r. What's the opposite of multiplying by t? Dividing by t. So I need to divide both sides of the equation by t. The right-hand side by t and the left-hand side by t also. So now I notice t over t equals 1, so I get PV over NT equals R. Now the R is on the right-hand side. That's okay. We often write it by convention on the left-hand side, but we don't have to. This equation is in fact solved for R because R is by itself on one side. And if we prefer to have the r on the right, we can even rewrite it like this, r equals pv over nt. Either of these is okay in terms of writing our final answer. Let's try one more. In this case, let's solve for h. We've got the equation s equals 2 pi r squared plus 2 pi r h. Again, we've got a lot of other variables here other than the h for which we're solving, but that's okay. It doesn't need to be the only variable. It just means that what we want to focus on is that we want to get this h by itself on one side, so everything else needs to be moved to the other side. So, what do we need to move? Well, for starters, this 2 pi r squared, we could get rid of that. That's being added, so we could subtract it from both sides. So we have s equals 2 pi r squared plus 2 pi r h. And so I want to subtract 2 pi r squared from both sides. So I have s minus 2 pi r squared, and here on the right I have 2 pi r squared minus 2 pi r squared. That's going to get me 0. So what I end up with is s minus 2 pi r squared equals 2 pi rh plus 0, which just gives me 2 pi rh. Now again, I still want to get the h by itself, so I need to get rid of this 2 pi r. What is the 2 pi r doing there in the equation? What's being multiplied by the h? So what's the opposite of multiplying by 2 pi r? Dividing by 2 pi r. And I can divide both sides of the equations by 2 pi r. So I just divide both sides completely by 2 pi r, 2 pi r. Notice I divide everything on each side by 2 pi r. So for example, on the left-hand side I have two pieces. I have an s and I have a minus 2 pi r squared. Both of those need to get divided by the 2 pi r. So what happens? Well, I have a 2 pi r on the top and a 2 pi r on the bottom here. So that divided by that just equals 1. We divide anything by itself, we just get 1. So what do we end up with here? On the left-hand side, we have s minus 2 pi r squared over 2 pi r. We can leave it like that, or if we prefer, we can divide each piece by the 2 pi r. And here on the right-hand side, I have 1h left over. Notice here on the left-hand side, I have 2 pi r squared divided by 2 pi r. Well, the 2 and the pi, that will all cancel to get 1. And r squared divided by r will just leave me with an r over 1. So I'm going to get s over 2 pi r minus r over 1, which is just r, equals 1 times h, which is just h. Notice I've got h by itself on the right-hand side of this equation. So this equation has now been solved for h. If I like, I can even rewrite it as h equals s over 2 pi r minus r. Either way of writing is fine. Now, we may have noticed the equations we've looked at so far have been linear in the variable for which we are solving. What does that mean? Well, roughly, it means that while there may have been constants or other variables that were added to, subtracted from, multiplied by, or divided into the main variable we were focusing on, the main variable itself was not raised to a higher power or put under a radical or in other kinds of functions. For example, if we were solving for x in the equation, we pretty much just had x's in the equation, no x squareds or square roots of x plus 1 or anything of that sort. So more formally, how do we define a linear equation? Well, in this case, in particular, let's just define it for single variable equations. A linear equation for the variable x. You could, of course, have any other variable, but we're going to write out this one in terms of x. Is an equation that can be put into the form ax plus b equals 0 for some constants a and b where a does not equal 0. So what are some examples? Well, what's some examples of some stuff that is linear? 2x minus 9 equals x. That's linear. Well, it doesn't look like this form at ax plus b equals 0. It could be put into that form by subtracting an x from each side. This x on the right-hand side we could move by saying minus x, and we would get x minus 9 equals 0. Right? This is equivalent to x minus 9 equals 0, which is in that form. If you ask yourself what's the a in front of the x, you could just write it as a 1x. What's another example of stuff that's linear? Your example, negative 27 equals a. That may not look like it has the form. In this case, notice a is our variable, not x. Well, we could rewrite it in that form by saying 1a plus 0 equals negative 27. And then we can add 27 to both sides to get 1a plus 27 equals 0. That's definitely in the form here. 1 is the coefficient of our variable, and we're adding 27 to it. What about some examples of some things that are not linear? What would they look like? Well, for example, the cube root of y plus 6 equals 8. This square root right here, right away, is going to make it really clear that this is not a linear equation, because there's no way we can get rid of that square root to rewrite it in this form, ax plus b equals 0. Here's another example. P squared plus 9 equals p minus 4. We could try to rewrite this, but even if we move things around, we'll never be able to get it in the form ax plus b equals 0, or in this case, our x instead of an x would be a p. Because we've got this square. The fact that we've got this squared there means we can't rewrite it as a linear equation in this particular case. There are also other types of equations in a single variable where we might allow the variable to have higher exponents. So linear equations, for example, we don't allow the variable to have a square or cube or something else on it. But here's a common example of a type of equation that does have higher order exponents. A quadratic equation for the variable x Again, we could easily have the variable be a or q or any other letter. Is an equation that can be put into the form ax squared plus bx plus c equals 0 for some constants a, b, and c. Where we don't allow a to be 0. Right? If a was 0, it would just look like a linear equation. And the whole point of a quadratic equation is that we allow ourselves to square the variable. So again, let's look at some examples. So some things that are quadratic. Z plus 1 times z minus 9 equals 0. That's a quadratic equation. How can we tell? Well, we could multiply it out. Right? This is the same thing as z squared minus 9z plus 1z minus 9 equals 0, which of course we could rewrite as z squared minus 8z minus 9 equals 0. So we have our form. In this case, what is in front of the z squared? A 1. In front of the z is a negative 8. And then we have a plus negative 9. So this is quadratic. Here's another example. 8 equals 3x squared. This is quadratic. How do we know? Well, we could subtract the 8 from each side or subtract the 3x squared from each side. It doesn't really matter which we do. If we were to do that, we would get something like this. Negative 3x squared plus 8 equals 0. And we could even rewrite that as negative 3x squared plus 0x plus 8 equals 0. And here you can see we've got the form that we need. What are some examples of things that are not quadratic equations? Well, for example, if we took the cube root of 3a squared minus 1, we do have an a squared and whatnot in here, but this cube root here means there's no way we can rewrite it in this form, ax squared plus bx plus c equals 0. We're not going to have any way to be able to get rid of that cube root. Here's another example. 24p equals 2 to the p power. Again, we don't have a way to get that p out of the exponent here. So because the p is up in an exponent, it's not a quadratic equation. There's no way we could rewrite this type of equation in this form. A times p squared plus b times p plus c equals 0. It's just not possible. So now we might ask the question, since all the equations we solved before were linear type equations, what about quadratic equations? Can we solve quadratic equations? Like, for example, what if I wanted to solve this for x? X squared minus x equals 6. What could I possibly do? Well, my goal is to get x by itself on one side. But the problem that I run into is this x squared and this x. These are not like terms. So I can't put them together in any way. Even though I have all the x's over on the left-hand side, I don't have any way to put them together and get rid of everything else. So I'm kind of stuck. just using the techniques I've used so far, not going to get me where I'd like to go, which is to get x by itself on one side. So, how do we move on from here if we can't combine the x squared and the minus x? Well, we need to notice a neat trick. If we rewrite what we have, x squared minus x minus 6 equals 0, right, by subtracting 6 from both sides. Then we notice that we can factor the left side. So we get x plus 2, x minus 3 equals 0. So we factor the left-hand side, and the right side is 0. How does that help us? Well, we notice that two things can only multiply to get 0 if one of them is 0. So we have this pattern. We call it the zero factor property. But the name isn't so important as just recognizing what the pattern is. For any two real numbers, let's call them a and b, for example, we have if a times b equals 0, then this tells us that either a equals 0 or b equals 0, or both, of course. When we say a or b, we mean a or b or both. That's when we use the word or in math, we mean either one or the other, or both is possible. We can actually even generalize this if we're feeling ambitious. It's not just any two. We could say for any real numbers, a1, a2, a3, etc., up through an, any number we like. If we have a1 times a2 times a3, etc., times an equals 0, then this tells us that either a1 equals 0, or a2 equals 0, or a3 equals 0, or ... or an equals 0, or some combination. Maybe more than one of them is 0. Maybe they're all 0. All we know is at least one of them has to be 0. It's the only way we can multiply them all together and get 0 as the answer. So back to our example. We had it written down as x plus 2 times x minus 3 equals 0. So what does this tell us? This tells us that either x plus 2 equals 0 or x minus 3 equals 0. For each of those individual equations, I can easily go ahead and solve. Here I have the plus 2 I want to move to the other side, so I subtract 2 from both sides, and so I get x equals negative 2, or, and here I have a minus 3 that I want to move, so I want to add 3 to both sides, and so I get x equals 3. So here I have two possibilities, x equals negative 2 or x equals positive 3. Either one of those will work. And in fact, I can check that back in the original equation. The original equation, if you recall, was x squared minus x minus 6 equals 0. So x squared minus x minus 6 equals 0. And let's try plugging in negative 2 first. Negative 2 gets plugged in. Negative 2 squared is 4. Minus negative 2 is plus 2. Minus 6 equals 0. 4 plus 2 is 6, so I get 6 minus 6 equals 0. That certainly works. Let's try it again with 3. X squared minus x minus 6 equals 0. I go back and I plug in 3 in each spot. 3 squared is 9 minus 3 minus 6 equals 0. 9 minus 3 is 6. I get 6 minus 6 equals 0. That is also correct. So we can see that either one of these values will work. So to solve quadratic equations, or as we'll see other higher order polynomial equations, all we need to do is move everything over using our properties until we have 0 on one side. Then we can factor the other side completely and use this idea of the zero factor property to solve set each factor equal to 0 and solve. Let's look at some more examples. So let's start by solving for x. Let's suppose we have 3x squared minus 17x plus 10 equals 0. Well, this one's pretty nice because it's already set, the right side is already equal to 0, so if we can just write the left-hand side as a product, we're all set. And so all we need to do is factor the left-hand side. So I'm going to assume we remember how to factor pretty quickly. If we use one of our factoring techniques, we'll find we can rewrite this as 3x minus 2 times x minus 5. And you can check that. You can multiply this out. 3x times x equals 3x squared. 3x times 5 is negative 15x. negative 2 times x is negative 2x, negative 15 plus negative 2 is negative 17, and negative 2 times negative 5 is 10. So you can see that in fact it factors that way. So we can now use the zero factor property. In other words, we can use the idea that if we have a product here, first thing times the second thing equals 0, that means one of them has to be 0. At least one of them. So this means that either 3x minus 2 equals 0, or x minus 5 equals 0, or both. Now each individual equation I can go ahead and solve. The opposite of subtracting 2 is adding 2 to both sides. So cancel that to be 0. So I get 3x equals 2. And then I want to get rid of 3. The opposite of multiplying by 3 is dividing both sides by 3. 3 divided by 3 is 1. So now I get 1x equals 2/3. And 1x is just x equals 2/3. That's one possible solution. The other possible solution is just to add 5 to each side. So we get x equals 5. And we can check these by plugging them into the original equation. Let's go ahead and do that. I have 3x squared minus 17x plus 10 equals 0. Let's check that. 2/3 squared is 4/9. I'll write 17 over 1 times 2 over 3 plus 10 equals 0. So we write this as 3 over 1 times 4 over 9. 3 and 9 are both divisible by 3. 17 times 2 is 34. So we have 1 over 1 times 4 over 3 is 4/3 minus 34/3 plus 10 equals 0. 4/3 minus 34/3 is equal to negative 30/3 plus 10 equals 0. And negative 30 divided by 3 is negative 10 plus 10 equals 0. That's definitely correct. Let's check the other part here. We've checked the x equals 2/3. Let's check the x equals 5. So we have 3 times 5 squared minus 17 times 5 plus 10 equals 0. 5 squared is 25, so we have 3 times 25 minus 17 times 5 should be 85 plus 10 equals 0. 3 times 25 is 75 minus 85 plus 10 equals 0. 75 minus 85 is negative 10 plus 10 equals 0. We can see that that's correct. So the x equals 5 is correct. So we've checked our answers. Let's try another example. What if we have, I'm going to solve for a. We start with 12a squared equals 2 minus 2a. Well, we notice this is a quadratic equation. Just trying to get all the a's by itself on one side won't work because I won't be able to combine the 12a squared with the negative 2a, even if I'm able to get them both on the same side of the equation. So the only technique is to try to get everything on one side, get a 0 on the other side, and then try to factor things so that we can use the zero factor property. So I will try to move the 12a squared over to the other side. The only way to get rid of it and get a 0 there is to subtract it from both sides. So minus 12a squared minus 12a squared. So I will get 12a squared minus 12a squared is going to be equal to 0. And then I still have 2 minus 2a minus 12a squared. I need to factor the right-hand side of the equation. Well, there are several ways to do this. We often tend to write the a squared first. And so if I wanted to, I could rewrite this way. Negative 12a squared minus 2a plus 2. It might make it easier for me to factor. And in fact, I notice the minus 12a squared, I could factor a negative sign out already if I wanted to. I could say negative 12a squared plus 2a minus 2. If I go ahead and use a factoring technique, I can go ahead and factor this out and get 3a minus 1 times 4a plus 2. Now I know I can finally use this zero factor technique. If I multiply two things together and get 0, even if there's a negative sign out front, I know that one of them has to be 0. The negative sign is sort of irrelevant. 0 is neither positive nor negative, so multiplying 0 times a negative 1 makes no difference. I could, in fact, in a sense, divide both sides by negative 1. And so this is really the same equation as just saying 0 equals 3a minus 1 times 4a plus 2. How did we get from here to there? Well, you could think of just dividing both sides in a sense by negative 1 if you like, and that would certainly get us to this next step. So this tells me that I either have 0 is equal to 3a minus 1, or I have 0 is equal to 4a plus 2. So now we want to get a by itself on one side for the equation on the left and for the equation on the right. So what's the opposite of the minus 1? It's adding 1 to both sides. So I get 1 is equal to 3a. And then I want to get a by itself, so the opposite of multiplying by 3 is dividing by 3. So I divide both sides by 3. 3 divided by 3 is 1. So I get 1/3 equals 1a. And 1a is just a, so I get 1/3 is equal to a. That's one possibility. Or I can solve this equation on the right. The opposite of adding 2 is subtracting 2 from both sides. So I get negative 2 equals 4a, and then I can divide both sides by 4. 4 divided by 4 is just 1. So I get negative 1/2 is equal to a. So these are the two possible solutions. It's good for us to go ahead and double check them. So the original equation, 12 times a squared equals 2 minus 2 times a. I plug in 1/3, I plug in 1/3. 12 times 1/3 squared is 1/9 equals 2 minus 2 over 1 times 1 over 3. I can write this as 12 over 1 times 1/9, 2 minus 2/3. And 12 and 9 both have 3 in common. We can divide them both by 3. So 12 divided by 3 is 4. 9 divided by 3 is 3. So I get 4/3 equals 2 over 1 minus 2/3. 2 over 1, we multiply the top and the bottom by 3 to get a common denominator. We get 4/3 equals 6/3 minus 2/3. That's certainly true. 6 minus 2 equals 4. So we've checked the first one. A equals 1/3 definitely works. Let's check the second one. 12 times negative 1/2 squared equals 2 minus 2 times negative 1/2. Negative 1/2 squared is 1/4. 2 minus 2 over 1 times negative 1/2. I can write this as 12 over 1 times 1 over 4 equals negative 2 over 1 times negative 1/2. Well, negative 2 over 1 times negative 1/2, those are just reciprocals. So we just get 2 minus negative 1, because 2 over 1 times 1 over 2 is 1. And here, 12 and a 4, they're both divisible by 4. 12 divided by 4 is 3. 4 divided by 4 is 1. So we get 3 over 1 times 1 over 1, which is just 3. So we get 3 equals 2 minus negative 1 is really 2 plus 1. And that's definitely true. So A equals negative 1/2 also works. Let's try another example. This time let's solve for y. 2y minus 1 times y plus 3 equals 9. Now this almost seems easy to solve, except the problem is when we have some things we're multiplying together, we need what's on the other side to be 0. We notice this is not 0. So it's too bad we cannot use the method we already know so far without rearranging it. So what can we do? Well, we can multiply everything out on the right, and then we can move everything over to the left so that we get 0. So we need to go ahead and do that. 2y times y is 2y squared. 2y times 3 is 6y. Negative 1 times y is minus y. Negative 1 times 3 is minus 3. So if we put all that together, we get 2y squared. And don't forget the equals 9 on the other end. Plus 6y minus y is plus 5y. Minus 3 equals 9. Well, we want to get 0 on the right-hand side. So we need to get rid of that 9, so we subtract 9 from both sides. And so what does that get us? It gets us 2y squared plus 5y. Negative 3 minus 9 is negative 12 equals 0. Now we have the 0 over here on the right-hand side that we need. If we can factor what we have on the left, then we can use the 0 factor property. Notice that property does not work when we don't have 0, because we can multiply all kinds of stuff together to get 9. We could multiply 3 times 3, we could multiply 9 times 1, we could multiply 18 times 1/2. There are actually an infinite number of things we could multiply together to get 9. A lot of them might be ugly, they might be fractions, they might be decimals, but we can come up with a whole bunch of stuff that we can multiply together. The only way we can do this, we can use this property, this factor property, is if one side equals 0. Because we know the only way to multiply two things together and get 0 is at least one of those things is 0. So if we factor the left-hand side, we'll get y plus 4 times 2y minus 3 equals 0. And now we can go ahead and use the 0 factor property. This tells us that y plus 4 equals 0, or 2y minus 3 equals 0. Solving, we would get y equals negative 4, or solving on the right-hand side, adding 3 to both sides, we get 2y equals 3. Dividing sides by 2, we get y equals 3/2. You can take a second to work that out if you need to convince yourself of that. So here are two possible solutions, and we could check them, again, by plugging them into the original equation. We've got 2y minus 1 times y plus 3 equals 9. And if I plug in negative 4, I should hopefully get something that's true, if I've done my work correctly. 2 times negative 4 is negative 8 minus 1. Negative 4 plus 3 is negative 1. Negative 8 minus 1 is negative 9 times negative 1 equals positive 9. That's definitely true. Let's try this other one. 2 times y minus 1, and then y plus 3 equals 9. We plug in 3/2, 3/2. So we get 2 over 1 times 3 over 2 minus 1 times 3 halves plus 3. Let's make that 3 over 1 equals 9. 3 over 1, we want to get a common denominator, so we multiply the top and the bottom by 2 here. And here, 2 over 1 times 3 over 2. Well, both 2's can be divided by 2, 1 on the top, 1 on the bottom. So we get 1 over 1 times 3 over 1, which is just 3 minus 1. 3 halves plus 6 halves. So we get 3 minus 1 equals 2. 3 halves plus 6 halves is 9 halves. And 2 we can rewrite as 2 over 1 times 9 over 2 equals 9. We can see that that's the case. The 2 over the 2 are going to cancel. So that works. So we can see 3 halves also works. Let's try one more example. This time let's solve for p. Now this one is higher order. We don't just have squares, we actually have something to the 4th power. Well, that's okay. We can still use the same technique. We're still going to need to try to get everything over to one side so that we get 0 on one side. And then we can try to factor and see if that works. So let's give it a shot. I could say minus 27p squared minus 27p squared. P to the 4th and p squared are not like terms, so I can't combine them, but I can go ahead and rewrite this so that I get 12p to the 4th minus 27p squared equals 0. Now I can try to factor what I've got on the left. Well, I can certainly pull a p squared out of each of those pieces. Is there anything I can pull in common out of 12 and 27? I can certainly pull out a 3. So let's give that a shot. If I factor out 3p squared, what do I have left? Well, I have 4p squared minus 9 equals 0. And I notice that the 4p squared minus 9, that's a difference of squares. Right. This is really 2p squared minus 3 squared. So I can rewrite that as a difference of squares as 2p plus 3, 2p minus 3. Now I've got 3 factors here, so I need to set them each equal to 0. So I have 3p squared equals 0, or 2p plus 3 equals 0, or 2p minus 3 equals 0. And if I solve each of those, here to get p by itself, I could divide both sides by 3. Well, 0 divided by 3 is just 0. So I get 3 divided by 3 is 1. So I get 1p squared equals 0. Well, the only thing I can square to get 0 is 0. Here, I can go ahead and subtract 3 from both sides. So I get 2p equals negative 3. And then if I divide both sides by 2, I will get p equals negative 3 halves. Similarly here, if I do the solution, I will get p equals positive 3 halves. Again, just as with the other problems, I can check out each of my possible solutions. I have 12p to the 4th equals 27p squared. If I plug in 0 to each of those places, I definitely get 12 times 0 equals 27 times 0. I get 0 equals 0, which is definitely true. Let's try the next one. 12p to the 4th equals 27p squared. And I put in negative 3 halves, negative 3 halves. Negative 3 halves to the 4th, well, let's see. The negative times itself 4 times, it's going to cancel out because it's an even number of negatives, so it's going to be positive. 3 times 3 is 9, 9 times 9 is 81, 2 times 2 is 4, 4 times 4 is 16. When we square the negative 3 halves, again we're going to get positive. 3 times 3 is 9, and 2 times 2 is 4. We can simplify some of this. So for example, 12 and 16, they definitely have 4s in common. 4 goes into 12 3 times, 4 goes into 16 4 times. So I get 3 times 81, 3 times 1 is 3, 3 times 8 is 24, divided by 4. 27 times 9, if we check it out, we'll get 243 divided by 4. So that works. Negative 3 halves works. We can try the same thing again. Positive 3 halves. We'll see it's actually going to go just the same way as it did with the negative 3 halves, because when we take the 4th power of positive 3 halves, we'll get the same thing as when we took the 4th power of negative 3 halves. When we square positive 3 halves, we'll get the same thing as when we squared negative 3 halves. So again, if we go through this procedure, we'll again get 243 over 4 equals 243 over 4. You can check that. So we can see that positive 3 halves is also a solution. So as we can see, we're now able to solve all kinds of equations. We can solve linear equations, we can solve quadratic equations, we can solve equations that have a bunch of different variables in them, other than just x or n or whatever the variable is that we're of interest that we're trying to solve for. And the main principle is that we just need to find a step-by-step procedure that allows us to replace each equation with an equivalent equation that has the same solution set